A new marker out here. So if we first understand where the heck, hold on, that if you see a charge in the top right corner, what do we call that? What do we call these things?
Ions.
Ions. So what are these called? The ones without a charge?
Atoms.
Atoms. Good. It's important to remember that. Positive ions are positive cation. The negative are anions. So you need to know the terms. Now, this atom has 19 electrons. This one has 18 electrons. Write that down. This has 17 electrons. This has 18. This has 16. This has 18. This has 20. This has 18. So, oops. This is just all from the worksheet there. And for fun, let's put the protons. 19 protons, 19 protons. 17 protons, 17 protons. The reason I'm doing this is so you really see protons do not change. All right. All right. Now, who can read me the electron configuration for all of the atoms up here? Who wants to do that? Who have I not talked to today? Morgan, I don't think I've called on you, Morgan Thomas.
Me?
Yeah. What's potassium? What's the electron configuration for K?
2881.
2881. Good. What about Cl?
287.
287. What about S?
286.
286.
2882.
2882. Very good. So we're all writing this down. I'm going to teach a whole bunch of things at once here. We're talking about radius again today. I didn't have you look those up. I should have. All right, so look those up tomorrow for tomorrow. I don't know if I have any other homework for you, but at least you can write those down somewhere, maybe in your notes. So those two words, atomic radius, ionic radius. K plus, Cl minus, S minus 2, Ca plus 2. All right, back to Courtney's question. Is there a reason why they're all 18? Well, I'm going to show you something here. The electron configuration, if you add up all these numbers, always equals what? The number of the total number of electrons. 2 plus 8 is 10. 10 plus 9, 19. 287, 17. 286, 16. 288, 20. So they always add up to the number of electrons, which makes sense because these are the electrons. What's with the dashes? What is it separating?
Levels.
Shells. Energy levels or shells. Good. What's the valence electrons? Or where are they? The last energy level, I'm going to just rephrase that, the outermost energy level. Okay, that's your valence electrons. You already know that. You don't have to write that. Okay. Everyone's good. No questions so far. Kind of just repeating things you already know, I hope. All right. Now, what's the charge on the nucleus?
Positive.
Positive. What's inside the nucleus?
Protons.
Protons, neutrons, aka all the mass in the nucleus. Okay, I'm going to be redoing the gold foil here. Positive nucleus, all the mass is in the nucleus. What else? Nucleus is dense. The atom is mostly empty space. Very good. So the nucleus is positively charged. Why? Because protons in it. Okay, good. Don't zone out on me, just reviewing. So, are the electrons attracted to the nucleus?
Yes.
Would positives and negatives be attracted?
Yes.
It's like opposite poles of a magnet, right? Everybody with me?
Yes.
Okay. So I'm leading up to learning some new stuff here. So if this here, I'm just going to underneath here kind of draw this atom. If I have the positive nucleus, just watch. I have 1, 2, 3, 4 shells. And I have 2 electrons here, 8 here, oops, 8 here, 8 here, and 1 here. That's kind of what this is showing. Does that make sense? Okay. Which shell or level do you think is more attracted to the nucleus than any other shell or level? Don't say it out loud, think. So shell number 1, number 2, number 3, or number 4, which shell, which energy level is more attracted to that positive nucleus, or has the greatest attraction for that nucleus? So think about it, and then raise your hand. Don't say it out loud. Which shell would be most attracted to the nucleus? Nicole, what do you think? The first shell. Why? Closest. Yes. Closest to the nucleus. So if I had, these are magnetic, okay? So if I hold it right here, it's going to be attracted. If I hold it here, is it attracted? Why? It's not close enough, right? If someone was holding a magnet in the back of the room, would that be attracted? No, it's too far. But if I'm very close, it's attracted. Does that make sense?
Yeah.
So the closer to the board, the more attracted this is. Electrons in the nucleus work the exact same way. Does anyone know where I'm going with this? Where am I going with this? When it's +1, it loses 1 electron. Which electron does it lose? One of those, one of those, one of those, or that one? That one. Why? Because it's less attractive. The nucleus can't hold it. The nucleus can't hold it. So this one is kind of free to come and go. Is it working?
Yeah.
Okay.
I just can't make mine work.
What's going on? Is it the same thing that YouTube capture?
Yeah, this got updated and I can't.
Now it's all messed up.
Yeah.
Did you delete all the old ones again?
Did.
From your deleted folder too?
Yeah.
I don't know.
But I kind of think you're on a different capturing program.
Oh.
So
Oh yeah, there is another one that
Yeah.
I downloaded before and didn't work as well.
I'll keep messing with it, and then when you get a chance.
Okay. So this electron here actually can come and go almost at will because the positive nucleus has a weak attractive hold on it because it's pretty far away. Does that make some sense? So here's what I'm trying to get you to learn. This is the configuration of neutral potassium. What would K+1 have? 288. So write that down. It loses the valence electron because it's not held together or held as tightly to the nucleus. The reason we're going to play tug of war, and surprise, surprise, I'm talking too much, but that's all right. We really have to understand first before we do that. The reason that we're playing that is that the nucleus is pulling on the electrons. But at the same time, the electrons are pulling back because they're negative as well. Right? Or they're negative, so opposites attract. So they're both pulling on each other, but the way it works in real life is the protons are way stronger. So they actually keep pulling those electrons in. But the further away the electron is, the less it feels that pull because there's other electrons between it. So the atoms always lose or gain electrons on that last energy level. That's where they lose or gain electrons, that valence shell. Yes?
Are they all 18 because they're all end up as 288?
Well, don't ruin all my fun, okay? What's the electron configuration of Cl minus? 288. It gains one here. Same explanation. The nucleus can't affect that level as well. It's further away. Guess what sulfur becomes? 288. Guess what calcium becomes? 288. Do me a favor. Copy all those down. Look at argon's electron configuration. Argon's electron configuration. Ariel's going to read it to us. 288. Argon has 18 protons, 18 electrons. 288. I didn't write that the same way, sorry. But it's all 288. What a wonderful thing. Put a little star somewhere in your notes. How about 2 big stars? I said little, make them big. They can be gold stars if you can read the lab correctly. So, 2 stars here. All atoms form ions in an attempt to gain a noble gas electron configuration.
Got it.
You got it?
Yeah, I just videotaped you and put it on there quick. I'll delete it.
Oh, good.
Yeah,
All right.
good.
Perfect. All atoms form ions in an attempt to gain noble gas electron configurations. And I'm going to put comma. It's called a complete octet. Put that in quotes there. All atoms really, really want to have 8 valence electrons. The way they can do that, this is a great example. These 4 examples here, the way potassium gets 8 as the last number is by losing 1. But Cl isn't going to lose 1 and get 8. It's going to gain 1 and get 8. Sulfur is going to gain 2. Calcium is going to lose 2. So it depends on where they are. It depends on their charge, and does it benefit them to lose or gain electrons. So here's the goal. This is the theme here. You need to memorize this. All atoms on the chart really want that complete octet. And I'm out of room, but I want to add one more thing to this. The reason, so your question led to a really great discussion there. This is actually a huge, huge concept in chemistry. This is why if you take sodium and put it in water, it explodes. This is why. Because it wants a complete octet. It wants that 8. So any reaction you ever see, this is why. So one more thing here, put underneath there. 8 valence electrons. 8 valence electrons makes the I guess we'll say ion very stable. Very stable. Very stable. So 8 valence electrons means very stable. Another way to word this, a little star here. Another way to word this, a better way, is a complete, I'm sorry, a full valence shell is very stable. And I'm going to explain more with this moving forward here. But it's important for you to understand that the way these ions work is that 8. But then this here, a full valence shell, that means 8. Full valence means 8. This is a better way to say it though. Here's why. Lithium. What? How many electrons does lithium have? 3. It can't ever have 8. It doesn't have enough. When lithium forms an ion, what ion does it form? Don't lose me here. Lithium, when it forms an ion, go to your periodic table. Plus 1. If I ask you what ion an atom forms, you go to your periodic table, look in the top right corner of the box. That's how you answer that question. You always look at that top charge. Okay? So the lithium atom forms a +1 ion. So if lithium forms +1, how many electrons does it have if it's +1? 2 electrons. The electron configuration goes from 2-1 to just 2. That's where this comes in. So for lithium, 2 electrons is a full shell. So it can never have 8. So this is a better way to say it because it applies to everybody up there. The 8 valence electrons only applies to elements above boron. So carbon and higher. So hydrogen, helium, lithium, beryllium, boron, the first 5, they can't have 8. So you just use this phrase, okay? But again, why am I going through this? Courtney asked a question. I was going to teach about it anyway. This is not a coincidence. They all have 18 because they all want to be like argon. They all want to have that full valence shell. And that is actually really important stuff there. Understanding a whole bunch of concepts. Can you tell me K +1 lost 1 electron? Can you tell me Cl- gained 1 electron? And then one step further, can you write the electron configuration and tell me why that's stable? And that's here. You have 8 or a full valence shell. Stable meaning it's not going to react. It won't react. That's what this means. Because we know noble gases don't react. They're inert. They don't react. All the other elements go through reaction so they don't have to react anymore. They become noble. That's kind of the way we word it. Questions? There's a lot going on there. Okay. How many electrons can the first energy level hold? 2. Look, they all start with 2. How many electrons can the third energy level, or second energy level hold? 8. How many can the third hold? I tricked you, it's not 8, even though 8 is considered full. What? Doesn't make sense. Oh, I know. Look it up. Look it up. Look at one of the elements with a lot of protons, a lot of electrons. Like look at bromine, for example. How many in the third level? No.
18.
18, right.
I thought you were talking about the second.
I'm talking about the third level. Third level. Third level.
Well, we got
Whoa,
elements that
Whoa,
have
we
eight.
got all
Yeah.
types of numbers.
They have 32 in the second one.
No, they don't.
So what
Is
that?
there a dash before the number?
Yes.
And that means it's not the second, it's the third. They're just not showing all of them.
What is this?
It's
Then why-
tomfoolery.
Then why is it 32?
Oh, yeah,
Yeah, for
there
answer
is one.
So it is 32.
Yes.
So I was right. 32.
Not in the third level.
You said that was you just said it was the third.
Look up here. Here's the order. 2 on the first, 8 on the second, 18 on the third, 32 on the fourth, fifth, sixth, seventh. So it goes 2, 8, 18, 32, 32, 32. You do need to remember that. And I'm going to give you notes on it. I'm just bringing it up right now. Now I'm going to talk about the radius. So we'll talk more about electron configurations down the road. That was a good introduction. All right. Okay. Last thing here, end class. Oh, that was going to ring. Dang it. We didn't get to it. All right. We did a lot today, I feel like, so we'll kill it there. Plus, we're missing some people.
Everyone say hi.
You have no homework, I guess.
Smash that like button.
Say hi
Don't
to
worry.
everyone.
Who are we saying hi to?
So
Adam.
frustrating.
Hi, Adam. What about Mike and Mike?
Remember to
Morgan?
smash that like button, Adam.
Yeah, but we're
Yeah,
not saying
they're-
hi to them.
They're on sports and med field trip.